Hello. Today I'm going to talk to you guys about collisions. Now, collisions can happen in a number of different ways, and just like a lot of things we talk about in physics, there's the ideal versions and then there's the real world versions. And because the class is the way that it is, we tend to stick with the ideal versions. So we're going to talk only about two different and pretty ideal versions of collisions today. So to understand that, I want to show you two situations here. So you've got let's say you're a little kid and you got went to the drugstore and you got a Super Ball and you got some Play-Doh, and you want to play around with those. So you decide to drop the Super Ball to see how high it bounces after it hits the ground. Of course, then you do the same thing with a lump of Play-Doh to see how high it goes up after it hits the ground. And I think you can tell just by those two that you're going to have two very different situations, two very different outcomes as a result of the collision between the object and the ground. Now the ground does get an impulse and it does change its momentum in a tiny way, but remember the Earth is really huge, so we're not really going to worry too much about the change in momentum of the Earth as a result of this. So Newton's third law is important, and we are trying to take that into account. But remember, the Earth is like 6 times 10 to the 24th kilograms, so a Super Ball doesn't change its momentum very much. So what happens? Obviously, we drop the Super Ball, it hits the ground, and it bounces back up. Does it ever bounce back up to the same height? No, it doesn't, but it does close, and that's why we call it a Super Ball, right? So maybe it bounces back up to a height of about this, right there. So it goes all the way down, bounces back up to right about there. So it loses a little bit of what we'll later on call energy because of its collision. But for the most part, the energy that it had before becomes the energy that it has later on. So it doesn't lose a lot of energy. So it hits and bounces, right? So let's think about that for a second. Initially, right before it hits, it has this velocity in this direction. So its momentum is in that direction. So its momentum is there, and then after it hits, right here, it's going up like that, and so it's now its new momentum. I should write that over there by it. There we go. Its new momentum is going upwards. So it had a pretty big change in momentum, I think you'd see, right? It went from going down to going up. So it's almost the same amount going down as it is going up. So if you want to think about it, how much does it have? So let's say you have a negative 20 and you want to go to positive 20. How much do you have to add to negative 20 to get to positive 20? The answer is 40, right? So it ends up being a lot of change. On the other hand, let's look at the Play-Doh here. And so the Play-Doh is dropped and it hits the ground, and what happens? It just kind of sticks to the ground, right? And so we have this lump of Play-Doh on the ground, and not very exciting, right? So right before it hits, it has a momentum that's downward. And then right after it hits, it's still there, still right there. It hasn't moved at all. So its momentum is 0. And so my question for you is this: if you have if you look at the changes in momentum for these two systems, the Super Ball system and the Play-Doh system, if you look at them, which one's going to have the biggest change in momentum? So the change in momentum here, I think you'll see, is much, much greater. That means much, much greater than the change in momentum here. So which one had a bigger impulse? Which one had to have a bigger impulse applied to it? Well, change in momentum is equivalent to impulse, and so we know that the impulse here must have been much, much greater than the impulse there. And so which one experiences a greater force or for a greater period of time, or both? And the answer to that is the Super Ball. I think I gave you an example in class where I said as a little kid I used to half fill up water balloons so that they would bounce. And why did I do that? Because I knew that the impulse was going to be much greater if it bounced, and just like the Super Ball. And as a result, it kind of stinged a little bit more to my little brothers. So stung a little bit more. That's better. There we go. Anyway, so the Play-Doh version, much less momentum change, much less impulse. It just kind of sticks. So this one, the kinetic energy actually goes back up, which we're going to talk about in the next unit. This one, the kinetic energy becomes thermal energy in the ground for the most part. And so it just kind of heats up the ground, so it goes away. But we'll talk again more about energy later on. So again, we're talking about ideal situations here. What are the two types of collisions? So you can see basically right here, you can see them. One is called elastic and one is called inelastic. And so you can think, okay, elastic is kind of rubbery, it's kind of springy. What does that mean? Which one do you think it probably is? The answer to that is this guy right here. When they bounce, it's an elastic collision. What's an inelastic collision? Inelastic would be no bouncing. And so in this case, we have. Okay, so let's imagine, hopefully you only have to imagine, hopefully you've never gone through it, but let's imagine a car crash. So a car crash, you're in a car, you're driving along, I don't know, this guy hits a wall. Crazy, right? It doesn't really happen that much very often. But let's say it happens here. So what actually happens? What kind of collision is this? Well, first off, you have to understand that the impulse that the car feels is balanced out by the impulse that the wall feels. So even though the wall doesn't really move, the wall is fixed to the earth, and so the earth actually gets an impulse itself. But again, the car's mass is very small and its velocity is very tiny, which means its momentum is very small compared to the overall momentum of the earth. So we don't really see much of an effect at all, ever, as a result of that. And so the question is this: what kind of collision is that? Is it elastic? Did the car bounce? Not perfectly. And did the car, was it inelastic? Did the car get crushed? Did it get become one with the wall? And typically it's not perfectly that way. It doesn't completely crush itself, right? That would be bad news for our little driver right there if the car completely crushed itself like the Play-Doh would have. And so we find that in the real world, objects collide in a way that's kind of in between these two. It's a harder mathematical situation to deal with, so we don't typically deal with it very often. Now, cars specifically have lots of safety devices in them to try to make the collision more inelastic. Why would you want to make the collision more inelastic? Well, remember which one had the greatest change in momentum, right? So the elastic situation has a huge change in momentum, and the inelastic has a very small change in momentum. As a result, which one has the highest impulse, right? So the highest impulse is this guy right here. The lowest impulse is that one. We want the driver in the car and all of the passengers to experience the lowest possible impulse so that they're as safe as possible. The way that we do that is by, we can't really change the momentum too much, right? We can't go from 60 down to a number that's not 0. So we have to be able to stop, is what I'm saying. But we can avoid bouncing, and that's the trick. If you bounce, then you have a much higher change in momentum, which means a much higher impulse. And so you try to make the car collision as inelastic as it possibly can be in the real world. How do you do that? You do that by making things crumple up. And so you've got a situation where the front ends of most cars are designed to get destroyed in a collision. So they're not designed to survive at all. It's not designed to make your car the easiest or cheapest to fix after a collision like it used to be way back in the 50s and 60s. Nowadays, it's all about safety. So they want to make sure that your car keeps you safe in a collision as much as possible. Now, we'll go one step further, and they say, okay, these crumple zones and airbags and seatbelts are all designed to change. So they're trying to minimize. So they minimize your delta P as much as possible by not bouncing, and then they maximize your delta T. Now, what does that do for you? Well, if you know you have a minimal delta P, minimal change in momentum, that also means a minimal impulse. So you have the smallest possible impulse that you can have, and then you maximize your delta T. Now, don't forget that the impulse is equal to the force times the delta T, right? So this change, the force that's experienced by the car and everything in it is multiplied by the time that it takes to collide, and that gives us the impulse. Well, if you have a minimum impulse and you have a maximum delta T, you have the smallest possible force that things can feel to be able to change their momentum in the way that they did during a crash. And so the whole point is to try to make your collision, if you're the passenger or the driver, to try to make your collision as long as possible so it slows you down over a longer period of time. The last thing you want to do is hit hard and fast and then bounce. And that's how people get hurt when they're not wearing their seatbelts off of the either the dashboard or the driver's steering wheel. So what happens is their head flies forward because of inertia, right? So their head flies forward, hits the steering wheel, and in a very short period of time, their momentum goes from this to this. And so they experience not just a large impulse, but they also experience a very short change in time, which means their force that they feel on their head is very high. And so that's where people get hurt with head injuries in cars. And that's what airbags specifically are designed to try to fix. Airbags take that delta T and they spread it out as much as they possibly can. We're going to do an engineering project where we're going to have to try to both minimize the delta P and maximize the delta T that a car experiences. And we're going to do that next week.